What if I told you the safety margin protecting every GPS signal, every weather satellite, and everything timed by satellite clock has recently collapsed by 97% and almost nobody noticed? A metric called the crash clock just dropped to 3.8 days. That's the time between everything working and the first satellite smashing into another at 7 kilometers per second. In other words, it's the window that separates us from a one-way trip back to the Stone Age. The researchers who built this clock won't use the word catastrophe, but after you see what the Sun did 6 weeks ago and what's coming this March, you'll understand why they don't need to. Something is very wrong with Earth's orbit, and it just got a lot worse. Stick around until the end and I'll promise you will never look at the sky the same way again. If this story has you hooked the way it has me, make sure to hit like and subscribe to the Skylab. Now, let's get into it. On January 26, 2026, a group of researchers updated a number. Just a number. A single data point on a website most people have never heard of. The metric is called the crash clock, the collision realization and significant harm clock, and it's maintained by the Outer Space Institute. It answers one question. If every satellite in low Earth orbit lost the ability to dodge right now, how long until the first catastrophic collision? The answer came back at 3.8 days. Let that land for a second. 3.8 days, less than 4 days between everything working and the first satellite smashing into another satellite at 17,500 miles per hour. Now here's the part that should make you sit up. In 2018, that number was 164 days, 5.5 months. The margin of safety that separates functioning orbital infrastructure from the first domino falling has collapsed by 97.7% in just 8 years. Not over centuries, not over decades, 8 years. And when we say safety margin, we're not talking about some obscure engineering abstraction that only matters to people in lab coats. That margin protects every GPS signal guiding every airplane landing tonight. It protects every weather satellite tracking every hurricane forming in the Atlantic. It protects financial transactions timed to the microsecond, emergency calls routed through satellite relays, the internet connections that billions of people now rely on in places where no cable will ever reach. When the crash clock ticks down, it's measuring the distance between an ordinary Tuesday and civilizational infrastructure failure. And here's the thing that made me stop scrolling when I first read this. 6 weeks before the crash clock was updated to its lowest ever value, the Sun hit Earth with the most powerful solar radiation storm in 23 years. We'll get to what that means. But for now, just hold those two facts next to each other. The buffer shrinks to less than 4 days, and 6 weeks earlier, the Sun reminded us what it can do. The researchers behind the crash clock defined something they call the danger zone, a threshold at 1.4 days where there's a 50% chance of collision within the first 24 hours of maneuvering loss. We are not in the danger zone yet. But at the current trajectory, that threshold could be reached within 1 to 2 years. We're watching it approach like headlights on a dark road. Now, before anyone says this is fear-mongering, let me be clear about what the crash clock is not. It is not a countdown to Kessler syndrome. It is not a prediction that satellites will collide tomorrow. It is not a doomsday clock. It's a stress test. A measure of how dependent we've become on everything working perfectly every single second across thousands of objects traveling at 7 kilometers per second, roughly 15,700 miles per hour. The number doesn't tell you when something will go wrong. It tells you how little time you'd have if something did. To understand why that number should concern you, you need to understand what happened to it. Because the decline from 164 to 3.8 wasn't a gentle slope. It was a cliff. The story the crash clock tells is one of false comfort turning into alarm, and the timeline reads like a slow-motion disaster that suddenly isn't slow anymore. 2018, 164 days. That felt safe, comfortable even. If every satellite lost control, you'd have more than 5 months before the math said something would collide. There was room to breathe, room to fix things. 2019, 119 days. SpaceX had just launched its first batch of Starlink satellites in May of that year. 60 satellites on a single rocket. The future of global internet, they said. The crash clock barely flinched. Still almost 4 months, no one was worried. 2020, 102 days. 2021, 62 days. 2022, 26 days. See what's happening? The number isn't falling at a steady rate, it's accelerating. Like a car rolling downhill with no brakes, every second it goes faster than the second before. 2023, 11 days. Then something curious happened. 2024, 6.8 days. January of 2025, 6.8 days again, a plateau. For a brief window, some analysts suggested the decline was leveling off. Maybe the system was stabilizing. Maybe the worst of the drop was over. It wasn't. June 2025, 5.5 days. January 2026, 3.8 days. The plateau was an illusion. The decline didn't level off. It accelerated again. Here's the math that matters. The crash clock dropped about 60% in the first 4 years, from 2018 to 2022. Then it dropped another 85% in the next 4 years. That's not linear degradation. That's the signature of a system approaching a critical threshold, the kind of curve you see in compound interest working in reverse, or in viral spread models, or in any system where each step makes the next step worse. And the engine driving that curve is no mystery. It's satellites. At the end of 2018, there were roughly 2,000 active satellites in low Earth orbit. By mid-2025, that number had reached at least 11,700. That's a 485% increase in roughly 6.5 years. And the primary driver is SpaceX's Starlink constellation, which now exceeds 10,000 satellites and accounts for approximately 2/3 of every operational satellite in low Earth orbit. But Starlink isn't the only player rushing to fill the sky. Blue Origin has announced plans for a 5,400 satellite mega constellation. China's Guowang program targets 13,000. Shanghai Spacecom plans 14,000. Amazon's Project Kuiper aims for over 3,200. Eutelsat OneWeb has 648 operational, with a second generation under consultation. The orbital population isn't stabilizing. It's accelerating from multiple directions simultaneously. And here's something the researchers themselves flagged that most coverage has missed. The crash clock uses only publicly tracked objects, things big enough and bright enough to be resolved from the ground. It does not account for non-trackable debris, objects too small to see but large enough to disable or destroy a satellite on impact. The researchers have explicitly stated that if non-trackable debris were included, the effective crash clock value would be lower than 3.8 days. The published number is the optimistic version. The real number is worse. Some space watchers have gone further, alleging that the true value may already be lower than what's published, arguing that satellite operators, particularly SpaceX, may underreport close approaches to avoid regulatory scrutiny. There's no direct evidence for this claim, but it highlights a structural issue worth noting. The crash clock relies on publicly available tracking data, and the completeness of that data depends on operators voluntarily sharing it. The model is only as good as the information going in. We got a concrete illustration of what the congestion actually looks like in December of 2025. A Chinese satellite launched on a Kinetica 1 rocket from Jiuquan passed within just 200 meters of Starlink 6079 at 560 kilometers altitude. SpaceX Vice President Michael Nichols said no coordination or deconfliction was performed. 200 meters at orbital velocity, roughly 7.8 kilometers per second, is a margin of about 25 milliseconds. That's how much time separated two functioning spacecraft from becoming a cloud of shrapnel. This wasn't a simulation. This happened 3 months ago. SpaceX, to their credit, responded to the congestion crisis. On January 1st, 2026, Nichols announced SpaceX will lower approximately 4,400 Starlink satellites from 550 kilometers to 480 kilometers throughout 2026. The reasoning: fewer debris objects and planned constellations at that lower altitude, plus an 80% or greater reduction in how long dead satellites take to fall back to Earth. It's a genuine safety move, but it's also an acknowledgement from the company that put more objects into orbit than anyone else, that the altitude where Starlink currently operates is becoming too dangerous. The company that created the crowding is now moving to escape it. If the current deployment pace continues, the low Earth orbit population could exceed 20,000 active satellites before 2030. At that density, the danger zone threshold of 1.4 days isn't decades away. It's years away, possibly months. But the crash clock measures stress. It doesn't measure what the system actually looks like under that stress. Minute by minute, satellite by satellite. For that, you need to zoom in, and the operational reality is staggering. Each Starlink satellite performs an average of 41 collision avoidance maneuvers per year. That number comes directly from SpaceX's own FCC filing. Generation 1 satellites average 37 per year. Generation 2 satellites average 44. With more than 10,000 Starlink satellites in orbit, that translates to over 410,000 maneuvers per year, more than 1,100 per day. Astronomer Samantha Lawler calculated what that means in real-time terms. 1 collision avoidance maneuver every 2 minutes across the full Starlink fleet. Every 2 minutes, somewhere above your head, a satellite fires its thrusters to dodge something. University of Birmingham professor Hugh Lewis added another data point that makes the scale even clearer. SpaceX conducted 144,404 conjunction risk mitigation maneuvers from December 2024 to May 2025 alone, a 200% increase from the previous 6-month period. The problem is not holding steady, it is accelerating in real time, and the pace of that acceleration is itself accelerating. When you broaden the view beyond Starlink to all mega constellations combined, a close approach, defined as 2 objects passing within less than 1 kilometer of each other, occurs approximately every 22 seconds. Within Starlink alone, every 11 minutes. At 7 kilometers per second, the window between too close and direct impact is measured in fractions of a second. The entire system holds together because of a 3-link chain. Every maneuver has to be precisely calculated. That's computation. It has to be communicated between operators and tracking systems. That's communication. And it has to be physically executed by onboard thrusters. That's propulsion. Remove any one of those 3 links, and the system doesn't degrade gracefully. It doesn't slow down. It fails catastrophically within days. That's not my speculation. That's the literal definition of what 3.8 days measures. SpaceX operates with a collision probability threshold of 3 in 10 million, 2 full orders of magnitude more conservative than the industry standard of 1 in 10,000. You can read that 2 ways. On one hand, SpaceX is being exceptionally careful. On the other hand, they need to be. The environment is so congested that even their ultra-conservative threshold generates a maneuver every 120 seconds. And here's where the coordination problem gets genuinely frightening. SpaceX can control its own satellites. Their autonomous collision avoidance system is, by most accounts, impressively effective. But when other operators launch without sharing trajectory data, like the December 2025 Chinese launch that passed 200 meters from Starlink 6079, even the best avoidance systems can be blindsided. The system requires not just technical precision, but geopolitical cooperation. It has the former. It does not reliably have the latter. Think of it this way. Imagine a highway where 10,000 cars are all driving at 17,500 miles per hour. Every car needs to change lanes 41 times a year to avoid hitting another car. If the lane change system goes offline for 4 days, at least 1 crash is statistically guaranteed. Now imagine nobody agreed on the traffic rules, and some drivers won't tell anyone where they're going. This system works today. It has worked every day so far. No catastrophic satellite-on-satellite collision has occurred in the mega-constellation era. But it has worked every day so far is the argument the turkey makes the day before Thanksgiving. The turkey has an excellent track record. Right up to the moment, it doesn't. The researchers behind the crash clock are very careful about what they're claiming and what they're not. And the distinction matters because it's the gap between their caveats where the real danger lives. Sarah Thiele put it plainly. A lot of people are claiming we're saying Kessler syndrome is days away, and that's not what our work is saying. Aaron Bowley added the necessary nuance. A lot of people's mental vision of Kessler syndrome is this very rapid runaway, and in reality, this is something that can take decades to truly build. The crash clock does not measure Kessler syndrome. It measures only the timescale to the first collision if all maneuvering stopped. It doesn't simulate the second collision or the third or the cascade. It makes no claim that a runaway chain reaction is imminent. The researchers themselves compare that first collision not to a Hollywood explosion, but to an environmental contamination event, more Exxon Valdez than Armageddon. The crash clock paper frames it this way. A single collision in this environment would generate debris that threatens multiple other spacecraft, raises operational costs sharply, and degrades the orbital environment for years. It's the match, not the wildfire. But the forest is very, very dry. There's an optimist's reading of all this, and it's worth stating honestly. The crash clock measures a worst-case hypothetical in which every satellite operator simultaneously loses all maneuvering capability. That has never happened. The system works. Collisions are rare. The existence of the crash clock is, in some sense, evidence that scientists are paying attention. And that's a good thing. Then there's the pessimist's reading, and it's equally honest. The crash clock measures the margin of error between operational normalcy and catastrophe, and that margin is shrinking at an accelerating rate while the consequences of breaching it are growing. A system that requires 41 maneuvers per satellite per year across more than 10,000 satellites, with close approaches every 11 minutes, is a system operating with extraordinary precision. And extraordinary precision is just another way of saying very little room for error. So the question stops being about whether the system can fail. The question becomes, what could make it fail? What could take the computation, the communication, and the propulsion offline simultaneously across thousands of satellites for long enough to cross the 3.8-day threshold? The answer is the Sun. And 6 weeks before the crash clock was updated to 3.8 days, the Sun demonstrated exactly what it's capable of. This is not speculation about what could happen. This already happened. January 19th, 2026. An X-class solar flare, in the most powerful category, launches a coronal mass ejection toward Earth. Most CMEs take 3 to 4 days to arrive. This one took 25 hours. The European Space Agency clocked it at approximately 1,700 kilometers per second. The speed itself was part of the danger. Satellite operators had a fraction of the normal warning time to prepare. The solar radiation storm that followed hit S4 on NOAA's 5-point scale. Severe. NOAA's Space Weather Prediction Center stated clearly, this was the largest solar radiation storm in over 20 years. The last time an S4 was reached was during the Halloween storms of October 2003, which caused power outages in Sweden and damaged transformers in South Africa. Space Weather Live ranked the January 2026 event as the third strongest radiation storm since GOES measurements began. Simultaneously, the geomagnetic storm reached G4, severe, the second highest level on the scale. NOAA notified airlines, the FAA, NASA, FEMA, NERC, and power grid operators. Aboard the International Space Station, astronauts sheltered in the most heavily shielded modules, Destiny and Zvezda. Auroras were visible from the Netherlands and Germany, and reports suggested visibility as far south as Florida and Texas. In orbit, the effects were immediate. Satellites across low Earth orbit experienced increased atmospheric drag as the upper atmosphere heated and expanded. Orbital position uncertainties, the confidence window operators use to predict where their satellites actually are, expanded to kilometers. Samantha Lawler described the dynamic during the May 2024 storm, and her words apply directly to January. Drag can change very quickly. During the May 2024 solar storm, orbital uncertainties were kilometers. With things traveling 7 kilometers per second, that's terrifying. Everything is maneuvering at the same time, which adds uncertainty. The January 2026 event was, by radiation intensity, more severe than May 2024. Sarah Thiele connected the dots to the crash clock directly. Collision risk during the first few days of a solar storm is significantly higher than under normal conditions because atmospheric drag shifts satellite orbits while simultaneously degrading the tracking data operators rely on to avoid collisions. The The January 2026 storm lasted multiple days. The crash clock buffer is 3.8 days. Those numbers are now in the same range. The duration of real solar events and the crash clock margin are converging. The hypothetical scenario the clock measures is no longer hypothetical in scale, only in outcome. But January was just the opening act, because the sun's most dangerous month is approaching, and the sun isn't slowing down. March 20th, 2026. The spring equinox. Most people associate it with longer days and warmer weather. In space weather, it means something very different. In 1973, researchers Russell and McFerran published a paper in the Journal of Geophysical Research explaining what's now called the equinox effect. Around the equinoxes, March and September, Earth's magnetic field aligns with the solar wind in a way that allows more energy to penetrate our magnetosphere. A door opens that stays partially closed the rest of the year. The result? The probability of geomagnetic storms roughly doubles during equinox periods. NASA solar physicist David Hathaway's 75-year study of geomagnetic data confirmed the pattern. March averages 6 days of high geomagnetic activity per month, twice December's 3 days. March is, statistically, the most geomagnetically dangerous month of the year. And March 2026 arrives with the crash clock sitting at its lowest recorded value and the sun still burning through the tail end of solar cycle 25's maximum. The sun's recent behavior has been anything but quiet. In early February 2026, sunspot region AR4366 became arguably the most active region of the entire solar cycle. Over a single 24-hour period, it produced more than 20 flares, including 23 M-class and 4 X-class. The strongest measured X8.1, some outlets recorded it at X8.3, making it the most powerful flare of 2026 so far. The sunspot grew to roughly half the size of the Carrington Event sunspot of 1859, the one that produced the most powerful geomagnetic storm in recorded history, and it was pointed directly at Earth. As of early March 2026, 6 active regions sit on the sun's Earth-facing side, 3 of them freshly designated. A massive prominence erupted near the solar North Pole on March 2nd. Activity has been observed from a region beyond the southeast limb that is rotating into view within days, meaning whatever it's producing, Earth will soon be in the firing line. Solar Cycle 25's prediction panel error bars extend the possible peak as late as March 2026. The sun did experience its first spotless days in 4 years earlier in 2026, which might sound reassuring, but the declining phase of solar maximum can produce storms every bit as powerful as anything during the peak. There's a piece of research that adds an unsettling layer. Velasco Herrera and colleagues published a new superflare forecasting study in the Journal of Geophysical Research in 2026. They identified 2 interacting solar magnetic cycles that concentrate superflare probability into specific windows. Their model maps the current high-risk window to mid-2025 through mid-2026. Exactly now. This is the same research that prompted recommendations to delay NASA's Artemis II crewed lunar mission until late 2026. And NASA listened. Artemis II, already dealing with hydrogen leaks and a helium flow anomaly that forced the SLS rocket to roll back to the vehicle assembly building on February 25th, now faces solar risk on top of engineering risk. NASA has since scrapped the 2027 Artemis III moon landing entirely, rescheduling crewed landings to 2028. When NASA postpones flagship missions because of solar risk, that is itself a measure of how seriously the threat is being taken. The period from now through late April 2026 represents a convergence without precedent. The most geomagnetically dangerous month of the year, arriving during late-stage solar maximum, with the crash clock at the lowest value ever recorded, and the orbital environment more congested than it has ever been. These conditions have never coexisted before, because the orbital environment has never been this crowded during a solar maximum. This is new territory. But what would actually happen if a truly massive storm hit? Not a January-scale storm, a Carrington-scale storm, the kind that comes once or twice a century. ESA ran the simulations, and the results will keep you up at night. The benchmark for worst-case solar storms is the Carrington event of 1859, the most powerful geomagnetic storm in recorded history. Back then, the most advanced electrical infrastructure on the planet was the telegraph network, and it caught fire. A 2013 study estimated that a repeat of the Carrington event today would cost between $600 billion and $2.6 trillion in damage to North American power grids alone. Research published in October 2025 modeled Carrington-level blackouts lasting weeks in vulnerable US regions, particularly the Midwest and East Coast. The European Space Agency conducted tabletop exercises at the European Space Operations Centre in Darmstadt, Germany, modelling what a Carrington-level storm would do to the current satellite fleet. This was part of preparations for ESA's Sentinel-1D mission, and the result was sobering. No spacecraft safety could be fully guaranteed. A storm of that magnitude would simultaneously heat and expand the upper atmosphere, dramatically increasing drag on every satellite in low Earth orbit. Overwhelm the tracking and coordination systems that make collision avoidance possible. All three links in the chain, all at once. We already have calibration data for what a lesser storm does. During the May 2024 G5 storm, severe by any measure but far below Carrington levels, more than half of all LEO satellites had to burn significant fuel to compensate for drag-induced orbit changes. GPS systems were disrupted. A handful of satellites were knocked out of their intended orbits entirely. Position uncertainties expanded to kilometers. A Carrington event would be orders of magnitude worse. The ESA simulations suggested it could effectively wipe out the operational capability of the entire low Earth orbit fleet. The crash clock was not designed to model a Carrington-level scenario specifically, but the researchers' underlying math implies that even a few days without coordinated maneuvering, which falls well within the duration of a severe geomagnetic storm, could produce collisions. A storm that disables control systems for 4 days would, according to the model's probability distribution, almost certainly trigger the first collision. The buffer is 3.8 days. Do the math. Sarah Thieler framed it in terms that are hard to argue with. The risk for collision within the first few days of a solar storm is a lot higher than under normal operating conditions. Even if you can still communicate with your satellite, there's so much uncertainty in your positions when everything is moving because of atmospheric drag. So if a storm disables the system long enough for the crash clock to run out, you get the first collision. But what happens after that first collision? The researchers won't call it Kessler syndrome, but the math doesn't care what you call it. Most people, when they hear Kessler syndrome, picture the movie Gravity. A chain reaction of explosions, debris shredding everything in orbit in a matter of minutes, astronauts tumbling through a storm of metal fragments. It makes for great cinema. It's also not how it works. Donald Kessler and Burton Court-Palais proposed the theory in 1978 while working at NASA. Their argument: at a certain density of objects in orbit, one collision generates enough debris to cause further collisions, which generate more debris, which cause more collisions, in an exponential cascade that renders entire orbital shells unusable. Not for years, but for generations. Classical models treated this as a slow process unfolding over decades or centuries. But those models were built before anyone imagined putting 10,000 satellites into a single orbital shell. The physics make it terrifying regardless of the timescale. A 1-gram piece of debris at orbital velocity carries the kinetic energy of a 2-ton rhinoceros at full charge. A 1-kilogram object can catastrophically destroy a 1,000-kilogram spacecraft. A single satellite-on-satellite collision generates hundreds to thousands of trackable fragments, and each fragment becomes a new projectile. The debris doesn't slow down, it doesn't drift away. At 550 kilometers altitude, it stays in orbit for years before atmospheric drag finally pulls it down. Recent papers have identified specific altitude bands already at risk: 520 to 1,000 kilometers. This is precisely the zone where the majority of mega-constellation satellites operate. Thieler noted that these altitudes may have already reached the potential runaway threshold, the point at which debris generation begins outpacing debris removal even without additional collisions. Here's a number that connects directly back to the crash clock. If satellite operators lose control for just 24 hours, one single day, current orbital density gives a 30% probability of at least one catastrophic collision. One day, 30%. That single collision seeds the cascade. Not immediately, not cinematically, but the researchers say irreversibly. The researchers' own framing is deliberately unglamorous. They compare the first collision not to an explosion but to an oil spill, an environmental contamination event that degrades the orbital environment for years to decades. The debris field grows, operational costs spike, replacement satellites must be launched more frequently, creating more launch debris, and the cycle feeds itself. It's boring and devastating, not exciting. The match? Not the wildfire. But the forest? The densely packed shell at 550 kilometers, where most of these satellites operate, has never been drier. And we already have a preview of what the first spark looks like. It happened in November 2025 aboard a Chinese space station, and it started with a crack. November 5th, 2025. Hours before the Shenzhou 20 spacecraft was scheduled to undock from China's Tiangong space station and return 3 taikonauts, Chendong, Chenzhongrui, and Wang Jie, to Earth, the crew discovered something that changed everything. A small triangular crack on the re-entry capsule's viewport window. Microscope inspection revealed long, thin fractures in the window pane. The suspected cause, a debris impact. Completely unanticipated, untracked, unavoidable. The consequences cascaded immediately. The crew was stranded for 9 days while the situation was assessed. They ultimately returned aboard Shenzhou 21, their colleagues' spacecraft. China emergency launched Shenzhou 22, uncrewed, 6 months ahead of schedule, just to restore a lifeboat capability to the station. An 8-hour spacewalk in December inspected the damage. The damaged Shenzhou 20 returned uncrewed on January 19, 2026. The same day, the S4 solar storm slammed into Earth. This was the most serious mishap at Tiangong since the station became operational. The detail that should haunt you is this: the debris that caused the crack was invisible to every tracking system on the planet. Aaron Bowley described the category it belongs to. The biggest risk on orbit is the lethal, non-trackable debris. This middle region where you can't track it, it won't cause an explosion, but it can disable the spacecraft if hit. This population is very large compared with what we actually track. This is the debris population the crash clock doesn't even account for. The 3.8 days figure is calculated using only trackable objects, and something from the invisible population just cracked a spacecraft window and stranded 3 people in orbit. There's a grim irony embedded in this story. China's 2007 anti-satellite missile test, which deliberately destroyed a weather satellite called Fengyun 1C, created approximately 3,500 pieces of trackable debris, many of which remain in orbit today. Some of those fragments may have been responsible for later threatening China's own station. In March 2024, a separate fragment hit a Tiangong solar panel, causing power loss and forcing spacewalk repairs. The debris environment is a commons problem where your own actions literally come back around to hit you. Shenzhou 20 is not an anomaly. It's a data point on a curve. The frequency of debris incidents is increasing. The first accidental satellite-on-satellite collision, Iridium-33 and Cosmos 2251 in 2009, generated roughly 2,000 trackable fragments. Russia's 2021 anti-satellite test produced over 1,500. The Long March 6. A breakup in 2024 added more than 700 fragments to Sun-synchronous orbit, which is critical for Earth observation and climate satellites. Each event adds to the population. Each addition makes the next event more likely. The crash clock was hit by debris too small to track. The crash clock only counts objects large enough to track. If the invisible population is large enough to crack a spacecraft window and strand 3 astronauts, what would it do during a multi-day solar storm when tracking systems are degraded and satellites can't maneuver? That question doesn't have a comfortable answer. Over 7,600 tons of human-made objects currently orbit Earth. More than 36,500 tracked pieces larger than 10 centimeters. Potentially hundreds of millions of smaller fragments. ESA reported that debris in low orbit increased 50% in the last 5 years alone, and their models show something chilling. Debris will continue growing for the next 2 centuries even if every rocket launch on Earth stopped today. The problem has already outrun the simplest solution. The worst contributions came from deliberate acts. The 2007 Chinese anti-satellite test, roughly 3,500 trackable fragments from destroying Fengyun 1C. The 2009 Iridium Cosmos collision, approximately 2,000 fragments, the first accidental collision between two intact satellites. Russia's 2021 anti-satellite test, over 1,500 fragments from Cosmos, 1408, which forced ISS crew to shelter in their return vehicles. The Long March 6, a breakup in 2024, more than 700 fragments scattered through Sun-synchronous orbit. Each event is a permanent addition to the ledger, and the ledger only grows. The removal capacity to offset this growth is, as of right now, effectively zero. The Kesim stochastic model estimates that 5 to 10 large debris removals per year would be needed just to stabilize low Earth orbit, at a cost of $500 million to $1 billion annually. Current operational debris removal missions in progress? None. ESA's ClearSpace 1, targeting a single discarded payload adapter, is planned for 2026. One mission, one object, against 36,500 tracked pieces and millions of untracked ones. The policy response has been equally thin. In 2022, the FCC shortened the required deorbiting timeline from 25 years to 5 years, a step forward, but one that only addresses end-of-life satellites and does nothing about debris already in orbit. In 2023, the first ever US space debris fine was issued, $150,000 to Dish Network for failing to deorbit EchoStar 7. $150,000. That's the regulatory answer to a multi-trillion-dollar risk. For a telecom company, that fine is a rounding error, a cost of doing business you wouldn't even notice on the balance sheet. The fundamental question no policy framework currently addresses is this: how many satellites are too many? No international treaty limits constellation size. No binding agreement requires operators to prove their systems can survive a severe solar storm. No mechanism exists to deny orbital access based on congestion risk. The orbit is being filled faster than governance can adapt, and the entities doing the filling have no incentive to slow down. Some critics frame mega-constellations as a form of orbital colonization. By filling low Earth orbit with proprietary hardware, companies like SpaceX effectively establish a kind of de facto ownership of orbital real estate, crowding out future competitors and other nations' space ambitions. Scientists have applied the tragedy of the commons framework to orbital debris, a shared resource being exploited for private gain until it collapses for everyone. The debris is accumulating. The removal capacity is functionally non-existent. The regulation is decades behind the launch cadence. And none of this matters unless you understand what you personally lose when the system breaks. That's where this gets real. When people hear satellite collision, they picture something happening up there, far away, abstract, someone else's problem. So let me bring it down to Earth, literally, because the crash clock isn't measuring a space problem, it's measuring a you problem. Start with GPS, because it's not just Google Maps. Financial markets use GPS timing to synchronize trades at microsecond precision. The entire modern financial system depends on satellite clocks agreeing on what time it is, down to the billionth of a second. Power grids use GPS timing to coordinate electricity distribution across continental networks. Without it, synchronizing generators and load balancers becomes a manual process prone to cascading failures. Your cell phone call doesn't drop when you drive between towers because satellites are keeping the timing. Aviation relies on GPS for instrument landing systems, air traffic control spacing, and approach procedures. And agriculture, GPS-guided precision farming controls tractor paths to centimeter accuracy. Some models estimate a 38 to 48% reduction in global crop yields without satellite-guided agriculture. Certain regions like Central Europe could face losses up to 75%. Weather forecasting would collapse to 1970s era capability within days of losing satellite data. That means no hurricane tracking with sufficient lead time, no tornado warning systems with the advance notice we've come to depend on, no flood modelling, no wildfire monitoring from orbit. Emergency services lose their primary coordination infrastructure. In a world that is simultaneously experiencing accelerating climate-driven extreme weather, losing the satellite network that monitors and predicts those extremes is a compounding disaster. The warning system goes dark just as the thing it warns about gets worse. Then there's internet and communications. Billions of people now depend on low Earth orbit constellations for connectivity, particularly in rural, remote and underserved regions. Here's the paradox that sits at the center of this entire story. The mega constellations driving the congestion problem are simultaneously the solution to global connectivity. The satellites we're worried about losing are the same ones that make modern life function. We built essential infrastructure in the one place where it can all be knocked out at once. Lloyd's of London estimated back in 2013 that a catastrophic collision cascade could generate losses exceeding $3.6 trillion in the first year alone. That figure is 13 years old and almost certainly conservative given the enormous increase in satellite dependency since then. The GPS network alone underpins an estimated $1.4 trillion in US economic activity annually. GPS timing and satellite communications are also foundational to modern military operations. Precision munitions, intelligence, surveillance, reconnaissance, command and control. A degraded satellite environment doesn't just affect civilian life, it reshapes the global security architecture. The crash clock doesn't measure an abstract space problem. It measures the distance between normal life and a world where planes can't land precisely, crops fail at continental scale, financial markets lose their timing backbone, weather forecasts go blind, and billions lose internet connectivity. That distance is 3.8 days, and it's shrinking. So with all of this at stake, why is almost no one talking about it? We monitor space imperfectly. That's a statement that applies in every direction you look. The lethal, non-trackable debris population, the objects too small to see but large enough to disable a spacecraft, may be the most dangerous element in the orbital environment, and we cannot observe it directly. The crash clock doesn't count it. The Shenzhou 20 incident was caused by it, and it's growing with every collision, every breakup, every abandoned rocket stage that slowly fragments in the radiation and thermal cycling of orbit. That incomplete awareness extends beyond our own orbital neighborhood. The week of March 1st through 9th, 2026, saw at least 6 asteroid close approaches. Asteroid 2026, DQ-10, passed at 3.9 lunar distances on March 3rd with no size data available. It was discovered too recently to characterize. Several objects that week carried 2026 designations, meaning they were discovered this year. Later in March, an asteroid designated 2014 TN-17, classified as potentially hazardous, makes its closest approach in over 100 years. None of these pose impact threats, but the pattern of late discovery mirrors the debris tracking gap perfectly. Objects arriving from certain angles, particularly the sun's direction, can be detected only days or hours before closest approach, or discovered only after they've already passed. Our awareness of what is near Earth is incomplete in both directions, for objects passing through our neighborhood from interplanetary space and for objects permanently circling within it. Small asteroids, roughly 1 meter in diameter, strike Earth approximately every 2 weeks. The planet absorbs about 100 tons of space material daily. We live in a dynamic environment and monitor it imperfectly, and the confidence we place in our tracking systems is greater than those systems currently warrant. No major government has issued a public statement on the crash clock. No United Nations body has convened on the convergence of orbital congestion and solar maximum. The conversation is happening in preprint papers, engineering forums, and specialized space weather communities. The infrastructure that civilization depends on is protected by a margin measured in days, and most people have never heard of the metric that tracks it. The silence has a logic to it, even if that logic is uncomfortable. The entities most capable of addressing the problem are the same entities profiting from filling the orbits. The regulatory bodies are outpaced by the launch cadence. By the time a new rule is drafted, hundreds more satellites are already up. The public doesn't understand satellite dependency viscerally enough to demand action, and the scenario remains hypothetical until it isn't. until the storm hits at the wrong time, or the maneuver doesn't execute, or the tracking data comes back degraded at exactly the wrong moment. The final section brings it all together. 3 threats, 1 window, 0 precedent. 3 threads have been running through this entire story, and right now, in March of 2026, they are all pulling tight at the same time. The first thread is the crash clock. It tells us the margin between functional orbit and the first catastrophic collision is 3.8 days and shrinking. The danger zone threshold of 1.4 days could be reached within 1 to 2 years at the current trajectory. Every month that passes with more satellites launching and more close approaches accumulating brings that threshold closer. The second thread is the sun. It has already demonstrated it can produce multi-day disruptions. It did exactly that 6 weeks ago at levels not seen in 23 years. The spring equinox opens the most geomagnetically dangerous window of the year in just weeks. New active regions are rotating into view. The superflare forecasting models place us inside the high-risk window through mid-2026. The declining phase of solar maximum is historically capable of producing storms as powerful as any during the peak. The third thread is the debris environment. Even a single collision contaminates orbital shells for years to decades. The removal capacity is 0. The debris population is growing on its own. The non-trackable fraction, invisible to every sensor, is large enough to strand astronauts and crack spacecraft windows. And we may already be past the density threshold where a cascade once started cannot be stopped. These 3 conditions have never coexisted before, not because the sun hasn't been active, it cycles every 11 years, not because debris hasn't been a concern, it has been since the 70s, but because the orbital environment has never been this crowded during a solar maximum. In 2018, when the crash clock stood at 164 days, the world had 2,000 LEO satellites. Now it has more than 11,700, and the services running on them have become load-bearing pillars of civilization: GPS, weather, communications, finance, agriculture, military operations. We went from a world where a complete loss of satellite control would produce its first collision in 5.5 months to a world where that collision comes in under 4 days. We did this deliberately in pursuit of global connectivity. We did it during a period of rising solar activity. We did it with no guarantee that the coordination systems keeping everything aloft will survive the next severe storm. The SpaceX paradox sits at the center of it all. The company moving 4,400 satellites to lower orbits to reduce collision risk is the same company that put most of those satellites there. SpaceX is simultaneously the largest contributor to the problem and the most technically capable of mitigating it. This is not a simple villain story, it's a tragedy of the commons unfolding in real time at 17,500 miles per hour. The machinery in orbit works. Today, every maneuver executes, every close approach resolves, every satellite dodges. The system performs with extraordinary precision because it has to, because there is no margin left for it not to. The question the crash clock forces us to confront is not whether the system can fail. It's what happens on the day it does. And for the first time in the history of human spaceflight, the answer to that question is measured in hours, not months. 1 maneuver every 2 minutes. 1 close approach every 22 seconds. 3.8 days of buffer. And a star that doesn't care about any of it.